Hello students, we are back with another session of electronic devices and today we are going to discuss on feedback amplifiers. At this time we all know that an amplifier is simply used to increase the strength of a signal. While amplifying, the signal strength of the input signal can be increased. The increased part includes information with some noise. This noise is introduced in the amplifiers due to their strong tendency of magnetic as well as electric fields. Thus, most of the high-gain amplifiers is liable in its output to provide noise along with the signal. In amplifier circuits, the noise level can be decreased with the help of negative feedback by connecting an output fraction within phase opposition to the input signal. In this session, we will discuss an overview of a feedback amplifier, its types and topologies. The feedback amplifier can be described as an amplifier which has a feedback lane that exists between output to input. In this type of amplifier, we need to calculate the sum of feedback that is given in the following amplifier. The feedback factor is assumed by the ratio of the feedback signal and the input signal. Now let's take a look at the Barkhausen criteria of a feedback amplifier. Now let's consider a fixed voltage, that is Vi, which is applied at the input of the feedback amplifier. The output that we get is V0, that is equals to V0 is equals to A multiplied by Vi, where A is the amplifier gain. The feedback network beta determines the feedback to the given input. So we can say V of f is equals to beta multiplied by V0, where Vf is the feedback voltage. Now by substituting the value in the above equation, we will get V0 is equals to Vi, and we already know that Vf is equals to beta multiplied by V0. For the oscillator, we want that the feedback should drive the amplifier. Hence, Vf, that is feedback voltage, must act as an input voltage. Therefore, we can say V of f is enough to act as Vi when A beta is equals to 1. You see, this feedback network voltage can be calculated as feedback voltage is equals to gain multiplied by beta Vi. The transfer gain of a feedback amplifier can be found by using the following equation. Beta is equals to V of f by V0, where beta is a feedback fraction, V of f is the voltage of feedback network, Vi is the voltage of internal amplifier. Now we will be discussing the types of feedback amplifier. This amplifier is classified into two types based on the feedback signal. The first one is positive feedback amplifier and the second one is the negative feedback amplifier. Now let's discuss both the types in detail. Positive feedback amplifier. When the feedback current or voltage is applied to increase the input voltage, then it is named as positive feedback. Another name of this positive feedback is direct feedback because it generates unnecessary distortion. It amplifies the original signal power that is used in oscillator circuits, but it is not often used in amplifiers. Now let's discuss about the negative feedback amplifier. When the feedback current or voltage is applied to reduce the amplifier input, then it is called negative feedback. Another name of this negative feedback is inverse feedback, and this is widely used in amplifier circuits. Now let's discuss the feedback amplifier topologies. Mainly there are four basic amplifier topologies to connect the feedback signal. For the current and voltage, feedback is engrossed towards the input in series or in parallel. These topologies are as follows. voltage series feedback amplifier, voltage shunt feedback amplifier, current series feedback amplifier, and current shunt feedback amplifier. Now, voltage series feedback amplifier. In this circuit, a part of the output voltage is applied to the input voltage in series through the feedback circuit. The block diagram of this type of amplifier is shown. We can see that the feedback circuit is placed in series by means of the input. When the feedback circuit is allied in series through the output impedance is reduced and the input impedance is enlarged due to the series connection with the input. Now, following with the voltage shunt feedback amplifier, in this case, part of the output voltage is applied to the input voltage in parallel with the feedback circuit. The block diagram of the voltage shunt feedback amplifier is shown in the figure. We can see that the feedback circuit is located in shunt by means of the output as well as the input. When the feedback circuit is allied in shunt through the output as well as input, then both the output impedance and the input impedance will be decreased. Current series feedback amplifier. Here the output voltage is applied to the input in series through the feedback circuit. The block diagram of the current series feedback amplifier is shown in the figure. We can see that the feedback circuit is located in series by means of the output as well as the input. When the feedback circuit is allied in series through the output as well as the input, then both the output and the input impedance will be increased. Now, we will discuss the last topology, that is current shunt feedback amplifier. Similarly, a portion of the output voltage is applied to the input in shunt through the feedback circuit. The block diagram of the current shunt feedback amplifier is shown in the figure. We can see that the feedback circuit is located in shunt by means of the output as well as the input. When the feedback circuit is aligned in shunt through the output and in parallel with the input at the same time, the output impedance will be increased, and because the parallel connection with the input impedance will be decreased. Well, that's all about this topic, and in this session we learned introduction to feedback amplifiers, Barkhausen criterion for feedback amplifiers, transfer gain of a feedback amplifier, types of feedback amplifiers, and feedback amplifier topologies. We will meet again with another topic of electronics engineering. Bye.